Here we are at one of the most impactful applications of linear algebra. I mean, like one of the most impactful things that you can do with linear operations. The title of this video, a series of videos for that matter, is Eigen decomposition. It's a very long, scary kind of looking word, but by the end of this video series, I don't know, a few bite-sized video series, I want to convey eigenvalues, eigenvectors, and principal component analysis, PCA. Why do I have this word? Because what's happening with PCA is that we're doing a decomposition, and how the decomposition can be important for us. But first, let's go ahead and I would like to start with introducing the scenario, right? So let me put the title. So today we will be learning PCA. So the title of this video is PCA. But I would like to, before I start, before it becomes math heavy, I would like to introduce a scenario in which that we would be something that we desire, right? So let's say scenario 1, right? In the scenario, you start with your data set, right? Your data set that you love. Your data set has samples that you collect, right? So these are, let's call these guys your features, and you have several samples, right? So you collect this one and another one and another one. So that's so you have a bunch of samples, like CSV table, and you have many of them, and that's how you start. And what is this data set? Well, you would like to solve a problem. Your problem is, let's say, churn prediction, right? So your customers keep leaving, and you would like to find why and when they are about to churn. So you have labels, right? So you have labels, ones and zeros. All of a sudden this becomes very much like a binary classification problem, right? So this looks okay, not a problem. But I would like to introduce one little complexity. The number of features, let's say the number of features is just too much. Or you collect many samples and you don't know if one feature is related to other, etc. So let's say you have 63,000 such features, and you do not wish to let go of any of them, at least in a non-educated manner, right? You would like to, if you're going to let go, you're upset. This is scary, and these are your samples. I don't know how many of them, but yeah, this is your problem, and all you want to analyze your data. You would like to at least maybe train a simple logistic regression model, right? So you would like something simple, like something like that. If you had such an x and you would multiply this x with W1, and you would compare it, add some other W0, and you compare it. If it is greater than 0, you call it C1, and if it is less than 0, you call it C2, right? Alternatively, you can have this number, right? So W1x plus W0, use your sigmoid and get the probability. Or, so you do not need to use only one variable. In the end, you have 63,000 of them. You can go ahead and multiply all of the x of i's with some wi's, and sum them. I equals 1 to God knows what, d. And this is the one that scares you, plus some W0, and then compare it with 0, right? But here's the part. So this number, the summation, is the alarming one. So like the number of variables, the parameters that you have to fit should be 63,000, right? So this is a scary thing, and you not only upset, you're also terrified and worried. So like here's this little tear, or I don't know, sweat. That's you're terrified, because in the end the number of parameters that you're going to fit should be 63,000, right? Well, you can argue, you can say that, well, I learned some lasso regression that makes me eliminate as many of them as possible, right? So you can just, like, this lasso regression is going to force the weights of many of these guys to be zero, but that's really not what you want, right? So you don't want to like arbitrarily eliminate those that are called linear. You would want maybe, hopefully, find a linear combination of these 63,000 of them, instead of just getting rid of some of them, or maybe a series of linear combinations of them, such that your model gives you a good classifier. So that's a need. That's like you would like to go from d dimensions to some lower dimensions, let's say k. Let's talk about another scenario. So maybe this makes it even more appealing. Let's say you're here, you're at in a communication link, you're at A, right? So this is you, and you would like to convey your messages to your friend at B. So this is your friend waiting for your messages, and then obviously your communication channel. By the way, this communication channel can be internet, like anything that's band limited. Like we all activate our internet services, so we know what bandwidth, like the speed of communication, means. So your friend says, okay, yeah, I'm ready, just send me your first vector. Okay, you say, I'm sending it, and you're ready, I'm sending it. So you say 0.25, the next one is 1.5, and the next one is 0.75. That's it. So you send 4 numbers, a vector of 4 numbers, and then it receives, and then, yeah, okay, good, okay, I'm ready, send me the next one. Because you can only send, let's say, 4 symbols, for numbers in a second. And the next one comes, okay, you ready? I'm sending it. So the next one is 0.5, 2, 1, 1.5. You ready? You got it? You ask. Yeah, I got it. Okay, yeah, send me the next one, your friend says. I'm sending it. Okay, the next one is 0.25, 1.5, 0.75. Okay. Next one. Okay, I'm sending it. It's 0.125, 0.5, 0.25, 0.375. And now your friend says, wait a minute. Wait a minute. Because your friend says, oh, I mean, like we're using all this bandwidth, we're sending all of these symbols, but the things that you're sending me, when I look at it, they're just multiples of the same thing, right? So like your friend is clever. He says like, yeah, like before you send your data, just can you please look at your data and understand that there's actually a pattern within your data? You do not really need to like send me the whole thing. And you say, yeah, okay, I'm listening. What do you propose? Okay, from the ones that I look at, I see that your data is actually multiples of 0.25, 1.5, and 0.75, right? Yeah, okay. And if that's the case, let me have it in my side, and you just send me, while you're sending, just send me 1, 2, 1.5. right? You just send me these 4 symbols and we speed up our communication 4 times, and I can then reconstruct here. So my friend then is recommending that I can actually encode these guys with an encoder and then transmit 0.5, and then my friend is going to know something about my data set, my data, like the nature of the data, and then my friend is going to be able to decode with their decoder, and then he will be understand it's like 0.125, 0.5, 0.25, and 0.375, right? So that's the data. And you said, yeah, that's smart and all, but you know what, like it's my data is sometimes like it's not exactly 2, it's 2.2001, it's 0.5, 0.3, etc. Like they're not exactly multiples of the same thing. Okay, it's okay if it is not. You say like just send me whatever the dimension, that's whatever the most important dimension, and then send me the errors, like if need be, right? So like here you see that this same mindset can be used to take the 63,000 to reduce it to not to 1 this time, to 128 with an encoder, and I send 128 to my friend, and my friend has the decoder that this person can get 63,000 back. So that would be amazing, right? And that's actually something that's happening. But here we're going to ask this question: encoder, decoder. So the pairs are called a codec, and the codec has something to do with the data it is transmitting or it is storing, etc. Right? So now the question is that we're asking, since the name of this class is linear algebra, can we have an encoder decoder that's linear, right? So can I have the dimensions that are linear combinations of my 63,000, and many of these linear combinations, I can get several different linear combinations, and the decoder will be able to get it back from 128 all the way to 63,000, and in the end, I'm not gonna lose so much accuracy, right? So that's the goal, and in the following videos we will see how this is PCA.